hello and welcome again. I just mentioned already that this talk is indeed being live streamed. In case you have questions and want to ask them, but you don't want your voice to be recorded, you can ask them on Discord, and Liz here will ask them to me in between sessions. So welcome again. We are going to talk about ZK Snarks, understanding the basics, the basic mathematics of ZK Snarks. I'm Anna Kaplan, and this is Liz Steininger, who will also talk in a second. Okay, so let's dive in. First of all, the material that I'm going to cover, I took an example and prepared it for this talk, took an example out of the so-called Moon Math manual, which we wrote. We're going to talk about it in the end, so in case you want to see, you can scan this QR code or go on this URL. It's version 0, so beware. There's a lot of typos, there might be errors. So yeah, there's no introduction yet, so it's just for this audience, for you to follow this talk. Okay, so let's dive in. What is the structure of this workshop? So first, we're going to answer the question of what you can actually prove in a ZK Snark, because we always talk about proofs in ZK Snarks, and I normally get the question, but what can you actually prove in a ZK Snark? What are statements that we actually can prove? The second thing we're going to look at is that we're going to introduce the most insecure curve, because we need a very, very small curve. It's very insecure for our pen and paper example, which we will then cover in our third section of this talk, or workshop as well, so please feel free to ask questions. We're going to do GOV16 prover pen and paper run-through that I prepared over that curve, and then in the end, we're just going to quickly tell you more about the material that is on that URL that I showed before. Okay, so let's dive in. So what can you actually prove in a ZK Snark? Do you guys have things that you would want to put in a ZK Snark? Does anybody have something that they really want to prove to somebody without telling them more? Maybe the time you woke up today morning, or something like that. It's not as I love that. The proof of knowledge of a discrete log is amazing. I prepared some examples because I thought it's 9 a.m. in the morning, second day. Maybe we're not so creative. So there could be a person who has all those ideas, for example, proving that they're over 18, which I have to do a lot, unfortunately. Then, for example, maybe the prover wants to prove that they know prime factorization of a given number. Or the prover would want to prove that they know the preimage to a given SHA digest value, or that they want to prove to somebody that the weather is really good in Las Vegas, but they don't want to, for some reason, take a photo of the weather or something like that. So can we put all of these statements into a ZK Snark or not? What do you think? Are all of these, can we put all of them into a ZK Snark? Who thinks yes? Amazing, I love that. Who thinks no? Okay, some. Yeah, so I thought no, but I'm happy to hear how, if so. So from my perspective, you have to transform some of these things. For example, the weather is really good is a very subjective statement, right? So I think the weather is really good. A lot of my friends think it's really bad and it's really hot and it's not really good. So a subjective statement, it's really hard to prove. And the thing I'm over 18 is something where we would need to transform that statement. We need to understand this identity first, and then also understand what it means to be over 18 and how we actually mathematically describe that. So it's written here in this English sentence, we could not be able to prove that, put it into a statement of a ZK Snark. So the other two things, as you might see because they're longer, and there's a sentence of the prover knows, these can actually be maybe transformed in some way into a computational model which we can then prove in a ZK Snark. Just to remind you again, a ZK Snark, might have seen that already, is a zero-knowledge succinct non-interactive argument of knowledge. So one part, which I wanted to also show you here, is that we are always doing arguments of knowledge. So we want to show that we know something. It's not just that something is true, that a statement is true, but that the prover is going to say, I know a certain thing in regards to the statement. So beware of that. So we try to answer that a little bit, and let's see how we can actually transform these English sentences into something that we can mathematically then prove. What we are going to do is we have to translate this through several computational models. So we're going to start with the orange one. We are going to describe our mathematical but English sentence in an algebraic circuit. And then we're going to transform that into a so-called rank 1 constraint system, which is the green middle part. I'm going to describe that in a bit. And then we're going to transform that into a quadratic arithmetic program, or short QAP, which is like some polynomials. You'll see that in a bit. So let's start with an example, because I do want to do a pen paper run through. So our toy statement is going to be the 3 factorization of a number. So we have the number x4, and we're going to do all of that in F13. If you're wondering what F13 is, I hope you know how to read like the clock, not the digitalized clock. Then imagine it just has like another, it's not 12, but 13 numbers on there, and then you kind of know how to do modular arithmetics. That's a little fast, but if you want more information about arithmetics, we're going to, there's a whole chapter in this manual that I posted before on that, and a whole chapter on algebra. So if you want to understand how these kind of things work, like F13, things like that, there's a whole chapter on that as well. So we have the number x4, and we know that it has 3 factors, x1, x2, and x3. So we want to prove that we know 3 numbers, which if you multiply them together, will be x4. So how could this look like? So this could be something like that. We have a person, Paula, who's saying, I know x1, x2, and x3, such that their product in modular 13 arithmetic is x4. And then Vernon is like, no way, I can't believe you, that's crazy. And Paula is saying, yeah, but I won't tell you what x1, x2, and x3 are. And Vernon's very sad. This is a very non-practical example. This is not a practical thing that you would actually do in a ZK Snark, but just for us, that's good enough to see how graph 16 works. So this is kind of the idea behind it. So our goal is to prove an instance of the statement in a graph 16 ZK Snark over a BLS curve. Yay, let's do it. Okay, so we first have to transform this statement that I know 3 numbers multiplied to a 4th and F13 to an algebraic circuit. So let's do that first. Okay, an algebraic circuit. What is that and how does it look like? So when I describe it, it's a directed acyclic multigraph that computes somehow a polynomial over a field F. But in the end, we have to understand what we actually the kind of mathematical equation that we want to look at, and we have to transform it into something that has edges and nodes. And the nodes can be either variables or constants, or they could be multiplication or addition gates. So we'll have input nodes and output nodes, and edges in between which we'll label. So let's look at this statement. So x1 times x2 times x3, what we can do first is we can understand this in we have to understand what we do first. This is how you normally think about that, what part of that equation do you do first? So we'll introduce some kind of bracket notation, and then we introduce what actually the operation is that we're doing, and at this time we're doing a multiplication of x1 times x2, and then a multiplication of that times x3. So in the end, an algebraic circuit will look like this. In case you were just trying to figure it out yourself, I hope you got to the same example, and if not, let me know later. But in case you were trying to draw the algebraic circuit. So as you see here, we have 2 multiplication gates and 3 input nodes and 1 output node, and the edges are all labeled, and we have witness edges and instance edges. So that's what the W stands for and the I stands for. So we described now our equation as an algebraic circuit. And we have to continue, we have to understand this a little bit better, because right now I just showed you some kind of graph, and you're just a little bit yeah, but how does that even connect? How can we prove something here? So I want to ask you if you think that this kind of circuit, this kind of graph, would be satisfied by by certain edges that we input. So for example, what I'm now giving you here is the statement S that you can see on the right side, and it has like 11, 2, 3, 4, and 6 as the instance and the 4 witnesses. So what would happen is that they would like here be the edges like labeled like that, would be then getting those inputs, and we would want to understand if the circuit is then satisfied in this like circuit assignment, if that's valid. So who think, like maybe you can look at it for another seconds, who thinks that is valid? And if that circuit would, if you, yeah, I see some hands up. And who thinks this is not valid? Okay, I also see some hands up. Okay, so I'm interested in like why you think it's not valid, because from my understanding, we're in F13, so the circuit is defined over F13. If we have this as statement and this is assigned to the circuit, if you evaluate, like if we have this assignment, this circuit is satisfied for this statement. Oh, okay. Yeah, I was already like, what? Okay. Oh, I'm so sorry. This was me. And now another example. Maybe you can have a look again and like see if like all like that inputs in regard to that multiplication gates and that outputs would actually like satisfy the circuit in regards for this statement. Is like if I want to like prove to you this statement, do you think I can generate a proof? Or maybe I can generate a proof, but do you think that this would be a valid assignment? Who thinks yes? Okay, who thinks no? Yay, okay, now we're all on the same page, because I thought I might have a typo, but I don't. So yeah, this is not a valid assignment, because as you see here, for example, 7 times 4, even in F13, would not equal 8. And also 3 times 2 does not equal 7. Okay, so this is somehow like a little bit intuition of like how circuits are, like what circuits look like, how they're satisfied for what assignments, and how we look at like several statements for several circuits that we look at, like that we get. Okay, and now we have to transform this circuit, as I mentioned, so this is the green part now, and we're going to transform that circuit into an R1CS. So a rank 1 constraint system, and how does that look like? That's a set of equations. So I try to draw that here. So in the upper corner, you still see our circuit for the statement, and then in the middle, you see that set of equations. And what we have is we have coefficients A, coefficients B, and coefficients C. And each of them can be assigned regarding to instances and witnesses. And a lot of people know the matrix notation, but I didn't want to introduce matrices in case this is not something that you've seen. So we're going to deal with the equations in itself. So we have so many equations as we have number of constraints. So we have to, like, when we now are going to like try to formulate this problem as an R1CS, we have to first understand how many constraints we have and how they're formulated. And we also have to understand how many instances, of course, we have and how many witnesses. Okay, let's dive into that. So this is what we need. And how many numbers of constraints do you think we have? Just stop me, like just shout stop. 5, 3, 17, 4, 2. Yeah. Yay, okay, somebody shouted yes. Yeah, we do have 2 constraints here. And we can, it's a perfect question. So we have 2 like application gates, and we can like, normally like how you would generate an associated R1CS from a circuit is that you go from the instance, like you look at the statement that you have, and you would go from the like the left edge, right edge, so W4 times W3 equals I1, and then you like go up to like you follow your statement. I just switched them around so it's easier to read, but this is our like 2 constraints that we have, and now we're trying to transform this into a set of equations. So let's see, like in the, like as you see for like constraint 1, for the A coefficients, we only only the third A is set to 1 for the first constraint, and for the second constraint, only the third, fourth B coefficient is set to 1 as well, and C5 for the first constraint is also set to 1, and similar to the second constraint. So this is how you transform your circuits into an R1CS. And why you want an R1CS, by the way, is because it's really easy then to understand, to check those instances and witnesses, those assignments, if we have pairing-based snarks, because we can like check it in the exponent. It's really nice. So this is why we do this. So in the end, this is kind of the R1CS that we get. And I marked in purple the ones which are not 0 in this case, the coefficients. Okay, one transformation made. We still have to understand how we get a quadratic arithmetic program for this instance that we want to prove. So what is a quadratic arithmetic program? Actually, it's like certain polynomials. We have to like generate certain polynomials such that a particular divisibility property is still valid for these polynomials. So that's why we first we have like a such called like target polynomial, and we generate those polynomials A, B, and C. And from there we get another polynomial which is divisible by T if for that statement the statement assignment is valid if you look at the circuit, the corresponding circuit. Okay. So I want to go a little bit into this. Let's see. So since we have two constraints, we are picking two arbitrary but invertible and distinct numbers from our field F13. So we're picking 5 and 7. And then we can generate a target polynomial, which looks like that for two constraints. So in the end, it will be like x to the power of 2 plus x plus 9. And then, okay, I'm sorry. And then we're generating the corresponding QAP. So how that works is we're taking R1CS that we've seen, and we now have to understand how we would get a polynomial. So first, we're going to do a Lagrange interpolation, but we first have to understand that that's why we picked the two numbers. For the first constraint, every number like A2 at number 5 is 1 corresponding to the first constraint. So this is kind of like the thing we try to understand as polynomials for these constraints, and from there we can actually do a Lagrange interpolation. And our polynomials are k minus 1, so constraints minus 1 of degree k minus 1. So in this case they're 1 because we have two constraints, and we're determining them on 2 points. So we know from Lagrange interpolation that most of them are 0, but A2, A5, B3, B4, C1, and C5 are not. So we're doing Lagrange interpolation, and we can look at the set for A2 that we have, which would be 5, 1, and 7, 0. That's in the middle of the slide there. So we can actually calculate A2 for x, and this is how we do it. We can we explain Lagrange interpolation in the manual as well, but I didn't want to go in this was the deepest I wanted to go in. So yeah, in the end we get for A2 6x plus 10. We're doing some F13. Yes.
Can the interpolation points be arbitrary?
Sorry.
Are the interpolation points arbitrary?
So I think they have to be in the field. Yeah, so I'm, yeah, sorry for that, yeah. Okay, yeah, and then we can also similarly do that for A5, and yeah, we can deduce actually, because we are evaluating them on the same values on 2 points, that A2 equals B3 and C5, and A5 equals B4 and C1. So the corresponding QAP would look like that. If that's a little fast, and sorry for that, yeah, please ask, please have a look at the manual again, and we can describe that in a second.
The purpose of the Lagrange interpolation is to select the convertible distinct points?
No, oh, I'm so sorry. No, this was just for the Lagrange interpolation. We need to we need to just get arbitrary points to then see how the polynomial would look like. That's the Lagrange interpolation, is to actually get those polynomials. Okay, so
Anna,
this is the QAP.
can you
Yes.
repeat questions so that the people on the
Oh
live
yes,
stream
I'm
can
sorry,
hear
I
them?
want to do that beforehand.
Thank you.
So the question was, if the Lagrange interpolation is to get the arbitrary points, on which you do that, on which you do then the Lagrange interpolation, and no, we just get the arbitrary points in F13 to then do the Lagrange interpolation to get the polynomials, if that makes more sense. Okay. So yeah, what we did here is we transformed algebraic circuit into an R1CS and transformed that into a QAP. So let's look how we can now, for this QAP and for a statement, generate a proof. To generate a proof, though, we need to first understand over what curve we do that. And what we did in the MoonMath manual is we introduced a very insecure curve. So let's look at that before we can actually do the proof and generate the proof itself. Okay, so we need a toy curve. And for that, what we have to think about when we think about the toy curve is that the toy curve should be pairing friendly. So, for example, be nice if it's in the Barreto-Lynn-Scott elliptic curve family. So we are going to generate it according to those statements. And yeah, we also wanted to have a very low security parameter. So what we mean by that is it should be very small and have very few points. So it's very easy to calculate it. So yeah, this is kind of the idea. So what we introduced is BLS 6.6 with embedding degree 6. And it looks like this, y squared equals x to the 3 to the power of 3 plus 6 for all in F43. We are doing that over F43, and since 43 in bits, it has 6 bits, that's why it's BLS 6.6. So that's how we call it, because that's how we normally do that for BLS curves. Yeah, so this is the curve that we introduced and on which we can now do calculations. And it looks like this. If you also think it's very pretty, then you're with me. I think it's very pretty. It's really nice. So yeah, this is BLS 6.6, 39 elements. And what we want to look at normally is the large subgroup of BLS 6.6. And this is how it looks like. Has 13 elements. And what we give you here is an exponential map. So we're going to look a lot at the logarithmic order. We're going to calculate everything in a logarithmic order because it's really helpful pen and paper calculations. And yeah, I wanted to do an example with you so you understand how easy it is to calculate in BLS 6.6 and how to add 2 curve points together. So for example, we want to add those 2 curve points together, and normally it's quite complicated. But since we can do this in logarithmic order, we can actually see that the first curve point is 6 times the generator, 13 times 15. So we use here yeah, you can also think about we use it here as a scalar, but yeah. And the second point that we have is 11 times that generator, so we can just use exponential laws, and so it's 6 plus 11, and that's over F13, that's 4, and so in the end, that elliptic curve addition would be 3528. So that was quite easy in case you ever had a look at different elliptic curves. Yeah, so this is how we're going to do calculations and all of that. So it's very easy, but we still put in a whole addition table because why not? It's really easy and it's really helpful, and we can use it now in a second. So yeah. And from that, we can actually do wheel pairings. And we're going to use that large subgroup. We're using the 13 torsion for G1. And we're generating G2. And I'm not going to go into detail because that would be a little bit too much for this talk. But what we can do is we can get G1 and G2 for the wheel pairing. And yeah, we can use logarithmic order. So it's really, really easy then to calculate pairings. Yeah. So let's do, yeah.
Briefly, what is a pairing?
Okay, so the question what is a pairing? That's an excellent question. So a pairing is actually like a function over like you take like an input, like as an input like G1 and G2, and you have a target group in which you like put that GT, and I don't have a slide prepared for that. I'm really sorry, and I can very much recommend pairings for beginners. That's a perfect like manual on pairings, and I don't want to like explain more because I think I don't have the words right now to like explain it like properly and correctly. But in general, you can think about it as like taking an input from G1 from one group, taking an input from another, and like putting that into a target group. And normally to calculate that, that's kind of complicated. So with like this less curve, we can actually do that faster and in a like for pen paper example, and in a faster way. Yes.
So the problem is at 13, and the curve is at 43.
Yes.
Is there a relationship between the two, or like does one have to be always larger than the other?
Okay, so the question was that we have, as a field, we're looking at F13, but as a elliptic curve, like the scalar field for that is F43, and how the relation is. And I also want to like recommend pairings for beginners for that, because I don't want to like dive in into that like more. If that's fine. Okay, cool. Yeah. So let's look at how we can actually do like how we can actually generate a proof in graph 16 for that over that curve, and we are going to look at 3 stages. There's a setup stage, which you've seen, maybe heard about, preprocessing stage, and prover stage, and the verifier stage. You can also like simulate proofs if you have toxic waste. Yeah, so that's something you can actually also do. But yeah, let's look at, we're going to concentrate a lot on the prover stage here. Okay, so first we still have to understand how to, like, what setup we would do. So first, like parameters, as I mentioned, F13, we have the groups G1 and G2, we have the wheel pairing, and we have the generators of those groups as the parameters we would have. And yeah, calculate is maybe wrong word, but we have to understand, like, we have to like think about a simulation. Like, we need like simulation trapdoor. And we then calculate a common reference string from that. And that simulation trapdoor is also called toxic waste, in case you ever see that. If somebody has that for your graph 16 setup, then they can just generate proofs without having actual like correct witnesses for like their statement. So yeah, don't tell anybody besides people here about this simulation trapdoor. Just joking. Yeah, and then we can actually like calculate a common reference string, and for our specific example. And as you've seen here, like what we normally do, like is like in this case we can just like use logarithmic order that I just like showed you before in G1 and G2, and you can calculate all these values. If you need like, if you struggle with these calculations, they're in a manual, but I also have like some more on my iPad, so feel free to come like back to me if you want to like calculate them through. But as you see, we just take in the values from tau and like alpha, beta, gamma, delta, and the evaluation point S, and we take our values from the QAP, the polynomials that we have, A0, B0, C0, and so on. And for 2 constraints, it would look like this, and for our, like in our setting, and this is the values that we actually get in the end. Okay, so this is just the setup stage, but as I said, we want to actually generate a proof. So as I mentioned, so far, we never talked about a statement itself. We just generated a QAP for this like general problem of like a 3 factorization of a number. But to actually generate a proof, we need an instance and a witness. So for an instance, we take 11, and for witnesses, we take 2, 3, 4, and 6. That was one of the examples we've seen before. And now we actually have to transform we actually have to generate a polynomial from this QAP. So think about QAP again, and this is the polynomial that we get that also should be divisible by our target polynomial. So we can insert those values. I know that the first line looks very intimidating, but it's just inserting values. We have the polynomials, and we're just inserting them here. So in the end, we get the polynomial x, just x power of 2 plus x plus 9, which is the target polynomial as well. So yeah, the target polynomial is divisible. Sorry, p is divisible by t. That's what happened. But yeah. So we have this polynomial p, and then we have to understand how we have to generate a helper value as well, and we're going to look at the quotient polynomial h. And in this case, since p divided by t is just 1, yeah, h is also just 1. So with input from the common reference string, we can actually we actually see that this is yeah, 2634. Sorry, this is a little bit fast, but feel free to, after a talk, come up and ask some questions. So after we generate this polynomial, we can actually generate the proof, which has these 3 values, and we can just insert it. So first, we are going to calculate we times G1, let's say. So this is taking in the witnesses times those values from the CRS. So they come from the CRS, and those are the witness values, 2, 3, 4, and 6 in this case. And if you do some math, which I wanted to let you do, but as you see, it's actually really easy in F13, you get that value as well. And we can do, yeah. So this is for the first value. For the next values, we have to the prover has to put in some randomness. So we are sampling some random points from F13 and putting them and using them here in our calculation as well. Same for those b values. And yeah, calculating those points. Okay, and this is our, yeah, another calculation that we are doing here using that quotient polynomial that we've seen before, using the randomness that we've seen before. Yeah, and I know this went a little bit fast, and I hope you can redo the calculations. But yeah, we do get a proof from that. And I can maybe show it again. So the first value is G1 power of A, which you've seen before. And the second point is, yeah, G1C. And the third point is an element from G2. So yeah, as you've heard, maybe Graph 16 has these 3 elements in the proof. And there are 2 elements from G1 and 1 element from G2. So this is what we get in the end, actually, and we can actually calculate it by hand over our curve. So yay, we have a proof, and I thought that this is going to be we won't have that much time. So I wanted to give you the opportunity to do the verification. So we have the proof, and you can now play the verifier and try to do this calculation here. And yeah, that's kind of a homework from this workshop. So have fun with that. So this was kind of the pen and paper run through that we wanted to do. I know it was a little bit fast, and it was a lot of equations. I hope you got an intuition for Graph 16 and how things worked, and how easily if you use, for example, this toy curve that we showed exists, you can actually do really easy calculations and use logarithmic order for that. There's more examples in the book as well. And Liz is going to speak about the Moonmuff manual, where we're going to talk about the structure and all of that. Wow.
Thanks. Hi. Thanks, everyone. I just want to tell you a little bit more about the Moonmuff manual. So Anna mentioned in the beginning that we've been working on this.
Cool. So thanks a lot. So yeah, I hope what you've seen is that we first talked about what we can actually prove in a SNARK and how we go through this different computational models. Then we looked of how this very insecure BLS curve would look like. The whole construction is in the manual, so have a look at that if you're interested. And I tried to show you that those calculations that a prover does are actually not that complicated, and you can actually do them by hand. So that was what I tried to show you as well. And yeah, there's more explanations on formal languages and arithmetics and algebra and elliptic curves in the MoonMath manual, and a lot more examples. So yeah, I hope you like the talk. Thanks a lot, and yeah. Yeah, I think we do still have some time for questions, but yeah, we can also take it to, if you want to come up and go through the equations, I think that's a little easier. I was not sure of how, the workshop concept would translate to this room and to, this audience being live streamed. So, yeah. Yes?
It's about something on your slide.
Yeah, great.
Can you go to your clarification slide?
Yes, sure.
Super fast.
I'm so sorry.
Okay, so you define big A, big C, but there's little a, little alpha, and beta.
Yes.
Like,
I'm so.
I think I forgot what those were.
Yes, of course, yes, because that was more of a have fun slide. You're absolutely correct that you forgot to what they would be or how it would look like. So we have to prove that's the values up there, and we have to verify now the left-hand side and the right-hand side of this equation. So the question was, what are those values and how would I actually calculate that, I guess. Okay, so the alpha, beta, gamma, and delta values are actually those ones that we have seen in the simulation trapdoor. But, as I've mentioned, that's toxic waste, so we don't know that. But those values, so g1 to the power of a and g2 to the power of b, that's on the right-hand side, the first factor on the right-hand side, g1 to the power of a, to the power of alpha, and g2 to the power of beta are actually part of the CRS. Common reference string. I can go back and show you. Sorry. I did a lot of calculations on the slides. Okay, here we go. So this would be the first two values that I've written here in the CRS, alpha times g1 in logarithmic order, and beta times g1, for example. And it's similar for the other values for those. Okay, well, I'm sorry. Yes, and it's similar for the gamma, g2 to the power of gamma, and g2 to the power of delta, and g1 to the power of c is part of the proof. So, and for g1i, this is what is the second equation. So g1 to the power of I is what we like calculate here. And as you like this whole like things are also part of the CRS. So g1 to the power of beta times a0 s plus a plus alpha times b0 of s and plus c0 of s divided by gamma. That's also part of the common reference string. So those factors are part of the common reference string, and we like take those to the power of I1, the instance, the public value that we have. Does that help? Okay, yeah, so I is the instance values. So there's like I1 and IN. Yes, and we defined G1I, sorry, yeah. We defined G1I as this value. So we only have I1, so it would be 11 in this case. I also have the calculations actually written down. So you can absolutely come to me in a second. I can just like show you how you would do that. I just thought we won't have that much time, so I didn't put even more equations on the slides. Okay. Okay, yeah. So feel free to come. Ah, yeah, sorry, there's another question.
You mentioned earlier with the toxic waste, you can prove anything without
Yes. That's also like really like nice question actually. So yeah, so the question, sorry, yeah, I'm always forget to repeat the question. So the question was, like, with, like I mentioned, with toxic waste, you can also just like generate a proof that would verify. And how would that work? And for that, we can like look into the equations actually. So we don't need like witnesses, and we can just generate, we can just use like those alpha and beta values to generate those. And yeah, I should have put them into the slides as well. Actually, I can show you an example if you want, like after the talk in a second, or I can also post it in the Discord for everybody to see. I don't want to like right now dive into that and get something wrong, if that's fine. Okay, yeah. Okay, yeah, sure.
Thank you, this was excellent. Could we see again the drawing of the curve?
Yes. Sure. Oh, 1 second.
I am that big of a visual person, and I apologize. Thank you.
Sure. Yeah, so thanks a lot for coming to this very, like, just try to do a pen and paper example of graph 16 proof. Sorry if it was a lot of calculations, but please feel free to come up and we can like go through our calculations a little bit slower. Yeah, and so thanks a lot. And yeah, I think if there's more questions come up, I'll answer like on Discord, and I'll also put on the equations on Discord as well, the side equations that I have. And yeah, is there any more? Yeah.
Not so much a question, I just wanted to point out that the proof is often encoded in the other order, so if you encoded it as ACB, it's usually ABC.
Oh,
So
yeah.
it is a Zcash.
Yeah. Yeah, like the comment was that normally the proof is encoded in a different order. So yeah, it's normally ACB in Zcash. Just for if you like read about that again, and then don't get confused about that. Cool. So thanks a lot, everybody, and thanks a lot for being here for the first session.